In the next few videos, we're going to look at a number of different ways that packets can be routed across a network. In this video, I'm going to start with some of the basic concepts and principles of routing, regardless of whether we're routing packets based on their layer 3 or IP addresses, or if we're using the Ethernet address and Ethernet switches. The basic problem that we're trying to solve when routing packets is how should packets be routed from A to B? Should the path be picked by the end host A over here, by the network in the middle, or by some other entity? So what path should they pick, and what are the most important metrics for them to consider? Should they take the shortest path, the least congested path, a randomly picked path, the safest and most reliable path? Does it matter? So in the next few minutes, we're going to look through at some different techniques and some different metrics for solving this basic problem. So I'm going to look at a number of different approaches: flooding, source routing, forwarding table, and spanning tree. We'll look at some metrics, and then I'll describe what a shortest path spanning tree is, and then describe some other types of routing, multipath and multicast. Flooding is perhaps the simplest way to make sure at least one copy of a packet is delivered to every destination in the network, and therefore to the destination that it's wanting to go to. With flooding, each router is going to forward the packet to every interface. So if A is sending a packet, and let's say that it's sending it to B, so it has B's address in it, when it reaches the first router, it's going to send it out of every interface except the one through which it arrived. That's going to happen at the next router as well, so it'll send it out of these interfaces. It will come down to this one here, which will send it out here and here. Then it'll go out from here, and then it'll go from this one out of here. But it'll also go in this direction, and it'll come back around here and come back around here, and you can see very quickly that there's a loop that's going to form in the middle with the packet going round and round forever. But we can be sure in this case, because every packet will be delivered to at least once to every leaf. It will therefore reach every destination. And if it contains B's address, which it does, then we can be sure that B can find the packet or receive the packet by simply filtering on packets matching its address. This is clearly very inefficient. All packets are going to cross every link, potentially multiple times, and packets can loop forever. Therefore, it's common to use a hop count or a time to live field like we do in IP to stop packets looping forever. But at least we can be sure that packets are going to reach their eventual destination. We can be absolutely sure of that. So flooding is nice and simple. It requires no state in the routers. It doesn't require any understanding by A of the topology of the network. So it's very, very simple. But because it's so inefficient, it's really only used at times, at instances when we know nothing about the topology or we can't trust our knowledge of it. And we need to be able to reach every node. So we'll see a couple of examples of this later, particularly at times of transition when we're not quite sure what's going on. So, in summary, it's inefficient in link usage, packets can loop forever, and it's used when we don't know or can't trust the topology. Now let's look at another method called source routing. Source routing is when the source populates the packet with a sequence of hops that it will visit along its path. So if we give names to these routers, let's call them R1, R2, R3, R4, R5, and R6. And so if A is sending to B with source routing, it might, for example, put in the header R1, R3, R6, to indicate that it wants the packet to go through that sequence before it gets to B. So that would just say go to R1 first, go to R3, R6, and then to B. I just happen to draw them in the order in which they'll be visited. That's going to depend on the way in which we use source routing. We'll see that a little bit later. But it hits specifically here. A knows the topology. It knows the order in which it wants the routers to be visited. And it's giving the final destination to make sure that it works and reaches B. Likewise, with flooding, the routers need no forwarding tables to be populated in advance. All the decision-making is made by the end host. This is actually a pretty good example of the end-to-end principle in action. The function is implemented at the end host. A is the one that knew the route, and so it picked the path that would be taken. And this way we can make sure it's done correctly. But it's a lot of work for the end host, and packets are of variable length and might carry a lot of addresses. So on the face of it, it's kind of a good scheme, but clearly we would like to do something that was a little less heavyweight on the end host. So it's an end-to-end solution, no support needed from the network. Packet carries a variable and maybe long list of addresses. End hosts must know the topology and choose the route. And this is used when the end host wants to control the route. So now let's look at the method that we already know is used by the internet, and this is when we actually have a forwarding table that's used throughout the network to route the packets hop by hop. And as you know already, I'll go through this fairly quickly, if we're sending a packet from A to B along this particular path, S1, S2, S4, and then to B, with a forwarding table case, we use a forwarding table at each hop in order to decide where the packet will go next. So we've seen this example before. You can really think of this as an optimization. It's an optimization in the sense that although we could correctly have the behavior work by populating the packets with the route using source routing, we've decided to have the network take on this function to optimize it because it's such a common function, common to everybody that's using the network. So it's an optimization in the sense that the network is going to handle the hop-by-hop routing on behalf of everybody. It does require population of the forwarding tables, so we need a way to populate these forwarding tables. And we're going to see in the next few videos various ways in which we can populate this table. So from here on, we're going to be making the assumption that we're using forwarding tables and that that we need some method in order to populate this table in order to decide how the routing will take place. We have per destination state in the network because we are going to, for each of the destinations, we're going to have a next hop address populated in the table. Although we don't necessarily have to have per flow state. Any flows in the network that are heading towards the same destination can all use the same entries. When I'm populating the forwarding tables with entries, it's often the goal to create what we call a spanning tree. And we're going to see many examples of this. Spanning tree is spanning in the sense that it reaches all leaves, and it's a tree in the sense that it has no loops. So we want to make sure that we can reach every destination, or every source can reach a particular destination, and we want to make sure that there are no loops. Let me give you an example of this. Imagine that we want to create the spanning tree that A, B, C, and D, the hosts at the top, will use in order to send packets to X, the destination at the bottom. So A, its packets could follow this path, B's might follow this path, C's might follow this path, and D's might follow that path. So you can see I've created a tree with the root at X, and it's spanning all of the sources that might send to it. It's a tree in the sense that it has no loops. This would be implemented by populating the forwarding table at R1 with the entry, if I want to go to X, then I go to R3 as my next hop. That's telling it what to do here. Likewise, at R3, we would have an entry that said, if I want to go to X, then I will go directly to X. Similarly, over here in R4, I will say, if I'm going to go to X, then I'll go there via R7. So the spanning tree is used in order to create the routing entries so that we can populate the forwarding tables and therefore route paths along that spanning tree. When calculating the spanning tree, we need to know what our objective is, or what our metrics of success are. How will we know, amongst all of the possible spanning trees, which one we're going to pick? So this is going to depend on what our metric is. So let's look at some choices that we might have. We might choose to pick the spanning tree that minimizes the distance. This could be the geographic distance, or minimize the length of the links between the source and the destination. So for example, noticing that this link along here is long, we might decide that this path is actually geographically shorter than this one down here, and therefore prefer it. We might also choose the one with the minimum hop count. So the example I showed you before was generally following the shortest hop count. So for example, D would take this path here because it's the shortest number of hops. It'll also be the one that minimizes delay. I've got no way of telling directly from the graph what will minimize the delay, but that might be something that I can measure. In recent past, what have been the links that have experienced the minimum delay, and therefore give preference to those. I might use the ones that maximize the throughput. They may be the least congested, or the path that is least loaded. Or it may be the most reliable path, the one that in the recent past has failed least often. That may be my metric. It could also be the lowest cost path. I may have a price or a cost associated with using any one link, and I want to minimize it. Or it could be the most secure path, the one that most recently has had the fewest security attacks. Or it might be one over which I have a virtual private network running, and so on. There are many, many metrics that I could use. Or in fact, I could actually use a combination of any of those. So typically how we do this is we start by creating an annotated graph with whatever cost metric we've chosen, and I could have picked any of those ones. So we can represent our metric as a cost for using a link. So this is a set of costs that I made up, just as an example. In general, the costs might be different in each direction, just because of the congestion may be more in one direction, or the throughput may be different. But for ease of drawing, I'm going to show one number per link here. So one natural choice is to try to find the spanning tree from every host to X. And I might try to find the one that is minimizing the cost, and in which case I'm going to call it the minimum cost spanning tree. In this example, the solution is fairly obvious. Let's have a look at what that would be. So coming to X, if I'm coming from B, then the minimum cost is going to be to take that path here, because that has a cost of 4. When I'm going from C, the minimum cost is going to be this one here, which has a cost of 5, 3 plus 2. Coming from D, it's pretty easy. It's going to be down here. A is a little bit more subtle. It's not the one down here. The lowest cost one is the one that goes this way, which has a cost of 5. So there's my minimum cost spanning tree. And here's an example of that drawn out. So in this case, it's very simple to calculate it. What we need is a method that will work in much more complicated networks. For example, this one. This is clearly way beyond something a human could do in their head. This is a picture of the topology map for the backbone of the internet. Well, I couldn't do this in my head. Maybe you can. So we need automated algorithms to calculate the route and put the necessary forwarding entries into the forwarding tables in the routers. So to calculate the routes, the routers are going to exchange information with each other about the current topology as they know it. This is the job of what we call the routing algorithm, or the routing protocol. In some cases, the algorithm to calculate the route is wrapped in with the exchange of the state itself. In other cases, they're separate. We're going to look at examples of both. Going back to our outline, we've got down to the shortest path spanning tree. We're going to be looking at several examples of this over the next few videos. I just want to finish up by telling you about two other types of routing that are commonly used. The first one is multipath. So far, we've assumed that all the packets to a given destination are going to follow the same path, in particular the shortest path spanning tree. The downside of the shortest path spanning tree is that some links can become very popular. We saw that we had a path that went down here before and a path that went down here. You can see that this whole area here is going to become quite popular and could become congested. So it means we might need to keep adapting the algorithm. An alternative would be, instead of adapting the algorithm, is to, from the beginning, spread all of the traffic over all of the links. So this is quite different from the shortest path spanning tree. This might be a case where we send some of the packets from A to X this way, and we might choose to send some of them this way, and we might choose to send some of them this way, and we might choose to send some of them this way. This is called multipath, where we're spreading the packets to a destination over multiple paths. Essentially, we're load balancing traffic over some or possibly all of the paths. We're going to see the details later, but for now it's enough to know that it might look something like what I just drew. So in principle, it's okay for packets to take different length paths and to get misordered. So it might be that in the example I had here, that a packet taking this path here might get there much sooner than one taking this path here, and therefore get mis-sequenced relative to it. Now, the internet makes no promise of in-sequence delivery. That's the job of TCP, to put them back in the right order. But we're going to see later that in practice, it's common to make sure that packets within a given application flow don't get missequenced, just to make life a bit easier for TCP. But this is just really an optimization in the network. So multipath is when we spread the packets over multiple links in order to spread the load as evenly as we can across the network. Another type of routing, another method, is called multicast. So far, we've assumed that all packets are going to a single destination, something we call unicast. For example, the packets in the last few examples have shown them going from A to X as a single packet. In some applications, an end host might want to send packets to a set of hosts. For example, A might want to send packets to a single packet that gets delivered to B, C, and X maybe, but not D. Applications that might want to do this could be like a broadcast TV or radio station where currently B, C, and X are listening to a TV station being broadcast from A. It could be automatic updates to a large number of hosts. For example, a car company updating its inventory every night to all of its dealerships. Or it could be stock prices being updated in a trading room where you want everybody to receive the update very at the same time. So while we can obviously send each packet one at a time to its destination, that would be fine. A could send individual packets to B, C, and X. It's natural to ask if the network can help, whether it can and whether it should do the replication for us. So for example, A could send a single packet. It could come down until it reaches B, and then it could be replicated, one packet going this way, and one packet going this way, and another packet going on to C, and so on at every branching point within the network. So now we send one packet, and it's delivered to everybody, and we're using the graph structure of the network to do the replication for us. So notice that in order to send from A to B, C, and X, I've essentially drawn a spanning tree. And this is actually going to prove to be quite interesting later. I've got a spanning tree across the set of destinations. And we're going to see some examples of how this works later. It's enough for us to know right now that just that this is a one way of routing packets. And we'll see later how this is done specifically in the internet. So in summary, there are several ways to route packets across a network, starting with the simplest method, flooding. So in practice, we use routing algorithms, or also known as routing protocols, to calculate the routes and populate the forwarding tables. Often, the algorithms calculate the minimum cost spanning tree to the destination, and we're going to see lots of examples of that soon. Other types of routing include multipath to spread traffic over links, and multicast to deliver to multiple end hosts. That's the end of this video.